So I will repeat them in the case it's really needed that we will talk about anti paper and some application of it for coalescing Harris flows and triple collisions. And in particular, this is work in progress. So let's recall that a Harris flow in this infinitesimal covariance phi is a family of random mappings with values in square space such that everything in particle that starts from from X at moment S is just a Wiener process. Those Wiener processes are correlated, and phi describes the correlation. This process have independent and stationary increments as a family of mappings. It satisfies some good initial condition, so uniformly, and it satisfies the semigroup property in this sense. And the idea that I want to present is that one can use some barriers developed by Hesminski. It's very old, in his very old paper, one of his first papers actually. My translation of the title is Diffusion Processes and Elliptic Equations that degenerate on the boundary of a domain. And we can use those barriers to discuss the behavior of three-point motions in such coalescing flows. Hesminski includes singularity, that is coefficients that grow to infinity as degenerate coefficients too. So the object we are dealing with is fixed 3 points, ordered. We consider 3 points that start, 3-point motions that start from this exactly point of space. And we know that if we define these differences, eventually eta 1 or eta 2 becomes 0, that is, happens a collision, and we want to understand whether it can happen that eta 1 of tau equals 0 and eta 2 of tau equals 0 simultaneously. Or maybe there are regimes or curves along which this can happen, or maybe we can make a conjecture about along which lines or at which positions it can happen. Because we start with recalling that wait, there's another. Should be plus yx plus minus 1 minus x plus y d squared xy. So we have a process eta, and simply by the eta formula we have the standard, then we obtain this Dynkin representation for the operators of this form. So as you can see, it's not a really good function that needs to be investigated. This coefficient between the mixed derivative, it depends on x and y, that is eta 1 and eta 2, which are differences in the original formulation, in a nonlinear way. And for some reason, I lost a page. Like literally, I lost a page. Maybe even more than a page. Wait a second. I'm sorry. I don't know how this happened. And how. Something is wrong with the file, I'm sorry. I will stop sharing for a moment and we'll reopen it. Let me go to the end where I will. Oh, I know what happens. I'm sorry. Here what happened. It's, yeah, no, I'm sorry. It just went to pages mode for some reason and therefore the pages disappeared. Oh, okay, now it's proper. So this is the operator we are dealing with, and my interest in such operators was renewed when I learned about a very interesting paper by Drs. Pilipenko, Pavlikevich, and Ryasov, where they use some linearization of nonlinear situation by using them to study some membranes. So in the rest of the talk, I will consider a linearized version of this operator, because I hope that results that obtained for this simpler version, where we exclusively consider this phi, can be reformulated, can be transferred to the case of a general coefficient. So we consider this operator. The coefficients are unbounded, but because we are mostly interested in cases where points can be claimed to be non-attainable, though we can skip for a moment a discussion of what happens in infinity. And we switch to polar coordinates because now eta 1 and eta 2 live until the time any of it hits 0, so they live just in the first quadrant. We have this set, and we can then recalculate our operator to obtain these expressions, where here and everywhere C of phi just C just cosinus, S is sinus, S2 sub 2 is sinus of double phi, and this is this function. So we have nonlinear situation even in this case, and in this simple situation, which is going to be a model situation, we have simpler coefficients. Now, let's talk about the paper that was used here. So it effectively establishes some criteria for stability, attainability, regularity, and a point being repelling in the terms of elliptic PDEs, and what is most important, in the terms of barriers. And it should be noted that if coefficients of the original operator is bounded and uniformly elliptic on the whole set, including the boundaries, that regularity of a boundary point is equivalent to having a barrier, and having a barrier is equivalent to having a barrier just for Laplace operator, and barriers can be the condition of checking whether the barrier exists can be replaced with geometrical conditions such as external cone condition, external sphere condition, etc. However, in our case, the operator is degenerate singular, and that means that this geometric condition do not work automatically, and barrier should be constructed explicitly. Now, the original framework was two-dimensional situation where the domain D is surrounded by two parts of the boundary, gamma, this is some curve, piecewise smooth, and gamma 0 is just an interval on x-axis, and the operator can degenerate only on this part of the space. Everywhere else is uniformly elliptic and bounded. Now, since the original situation is bounded, definition, for instance, of a regular point that is going to follow should be modified exactly as Freilin's functional integration and PDEs, but I will skip this modification because we will not use the result for regularity. I still will cite it because I think it's an interesting, and there is not much information available for such Harris flows with correlation and so if we have a function given on a boundary or already an extension of this function on the whole closure of our domain, then obviously one can consider some exhaustion procedure to define such types of solutions of elliptic PDEs, and under good set of conditions, there exists a limit, and this procedure is known as the Wiener construction. And in modern literature, it's typically going to be written in terms of internal Schauder estimates, but we will not use the fact of the existence of the whole solution of the whole space. And obviously, we do not care about this part of the boundaries. This is just a regular part. Now, the point is called attracting if the set of limit points of this set, where tau epsilon is the moment our diffusion leaves this d epsilon. D epsilon is this. So we step slightly above gamma 0 where degeneracy happens. And if we have this, that limit points are almost concentrated on gamma 0, if we start close quite to gamma 0, is one, this point are called attracting. Such corrections are needed because we have this gamma near gamma 0. But generally speaking, obviously one can care only about like isolated point or subset of gamma 0. In the original paper, this correction is done because was one standard example of such bad operator when we have something going very quickly in this direction, independent of the behavior in this direction, in the way that it never hits the boundary, but it effectively covers, just ping pongs here until it stops somewhere on some boundary. And I will briefly just read through those results, and then I will explain what you can get in the case of Harris flows, because you cannot really get too much effectively. So the point is attracting if one of two for the point to be attracted is sufficient necessary for one of two conditions to work. We have a good sequence of solutions of the problem or corresponding elliptic problems in domains that form an exhaustion sequence for the original domain, or there exists a classical barrier that satisfies this inequality and goes to 0 uniformly near gamma 0. And the most interesting part is this barrier can be constructed in terms of the original coefficients by effectively taking a standard criterion for stability, for instance, as the one used in the book of Geekman's Korохod, though obviously at the time this paper was published, such book didn't exist. It was known to the author from literature, probably. You use the same construction, but you require, instead of just taking the behavior for fixed x, so what happens here, you require that something holds in this test uniformly with respect to the whole gamma 0. So this is here, and this is some enlargement in gamma 0. enlargement happens because we have this boundary behavior here, this gamma. And the barrier is constructed very easily. And the theorem goes, if this integrable, then gamma 0 is attracted. The point is called repelling if the probability of that attractive trajectories being attracted is less than 1. And again, one can formulate two conditions, one in the form of the sequence of solutions in subdomains, or in the form of a family of barriers of this form that still satisfy some good subharmonic condition. Here they are bounded from below uniformly when you approach epsilon, but they still zeros on boundary. And the stability test that is used here is again the same function, but now is minimum, and it should be not integrable, and these two expressions should be bounded, at least in some neighborhood of gamma 0. The reason why these functions are bounded is that the barrier is constructed as follows. And if you do calculation, you obtain something like this. And this condition guarantees that you can make the conclusion by obtaining this part and simultaneously this part. So obviously, as in most cases in this paper, you can theoretically do some reshuffling of this condition, maybe place have controllable growth, etc. A point is regular, obviously. If you start close to it, we hit boundary close to it. This is standard definition of a regular point. And the subset of this part of the boundary is called non-attainable if it cannot be hit for some starting point inside from the domain. And obviously, this immediately implies that it cannot be hit for any point. And composition of the a mixture of the result of Kosminski and, for example, book of Freilin on functional integration and PDEs gives a standard, a well-known condition of regularity in terms of barriers. This is one, now item 1, possibly locally. And so we lose geometrical condition like external cone condition, external sphere condition. We still have the condition of regularity even for degenerate or badly behaved operators in terms of barriers. And one can construct a barrier in the idea that was used by Kosminski, that one can use the Feller test whether the point is hit by the boundary point is hit by a one-dimensional diffusion. You can take the function from the Feller test and require that everything holds uniformly on some neighborhood of this x. So if you calculate this ZF, you will get almost the standard functions that is used in the Feller test with one correction. In the Feller test, this is 1, just. At least in all versions I am aware of. It's just 1, and then this is exactly the function. So again, it was used by Kosminski because then he can prove that the point is regular if this function is integrable, exactly as in standard formulation. And the barrier he invented is of this form, and if you do calculation and you calculate everything properly, you can see that you can actually use a classical Feller test to formulate a version of this theorem by getting rid of these two parts if you have some assumption of boundness of your coefficients. So you can formulate a version of this, of his result. And now the most important for us result is actually that the point, the part of the boundary cannot be hit if there is a family of barriers satisfying this condition. Now, C can be replaced by 1. So it's very similar to the repelling condition. It can be reformatted in terms of one single barrier that should grow to infinity near the boundary. And one do a similar composition, a similar transformation of the classical Feller test, but possibly switching minimum and maximum to obtain the result that this part of the boundary cannot be hit by our process if this function cannot be integrated near 0. And there are technical assumptions. In this case, this set should be split in 2. It's either that this coefficient ax doesn't switch sign, doesn't change sign, or it's bounded and the coefficient near this second derivative is separated from 0. Now, in our situation, if you try to use this theory, which I think, despite being very old, it's still very interesting because it really covers our situation, that neither theorems for attracting points for repelling points are not going to work. However, if we switch to the last version, so to this formulation in terms of these functions, we can actually do some stuff. And let's start with the case when alpha is just 1. And then one can prove that for any delta, this set, so the original gamma 0 in our case was just 0, P2. And this means that we need to exclude boundary and one point exactly in the middle. And then we can conclude that this set is not untenable. And obviously for that you just do formulation by using the version of the original paper or by using this corrected, not corrected, but modified version is a simple expression. And it's pretty much what happens when alpha is not equal to 1. So you always get all these functions that appear in all those tests in the form rho to some power multiplied by some expression that is maximum or minimum over some set of angles, and it's a ratio of two effectively exponential polynomials of this form, and then the function integrability of which we investigate is of this form. And as soon as this is well behaved, this function is not integrable. And all these exponential polynomials are, after change of variables, are polynomials of exponential polynomials of logarithms of tangents of phi or tangents of this expression, of logarithms of this expression. If alpha is rational, that it's very easy to check that it's actually a exponential polynomial of just this. But if alpha is irrational, it's not rational, you get both composition, but one proposition that you can prove that still the set of zeros, which is exactly the set where this function doesn't satisfy what it want to satisfy, that is the absence of integrability, is the set of these points where this function fails to satisfy this condition is a finite, which means that this exponential polynomial, or more precisely a sum of two exponential polynomials, have only finite number of roots. For that one can use the standard arguments that the signed measure have only finite number of switching keys. So and exactly zeros of such expressions is the problem with all these results of the results on regularity, the results on a point being repelling. So for instance, we need to check that this is bounded for the theorem of Vovchanskii to be applicable, but it exactly can be recalculated for alpha equal to 1 to this, and this is obviously unbounded exactly in the middle point. If alpha is not equal to 1, we will get multiple points where this is unbounded, but still only finite number of real roots. So the end result that we can formulate that for any alpha there is only a finite number of points such that if our eta hits the boundary, it can hit, there is only a finite number of points that eta can hit the boundary. So geometrically this means the following, that so we did this transformation eta 1, eta 2 into polar coordinates phi rho, and instead of leaving here rho, we switched to leaving on 0 to infinity. So this is rho now, this is our phi. And we know that eta 1, eta 2 can hit this boundary, which is exactly the situation of triple collision in the original formulation, only, for instance, if alpha equals 1, at this point, theoretically. Unfortunately, I don't know whether it's true, but I have some ideas how to approach the situation. So if we consider these points, this means that it's about hitting the boundary sliding along one of the axes x or axis y. So to investigate this situation, one can just discuss eta 1 in this situation, which is psi 2 minus psi 1. This is one-dimensional diffusion, which behave with this characteristic operator. So by switching to the Bessel process, we have some results on the behavior of such one-dimensional diffusions near 0, and we can try to draw a conclusion whether this is possible or not. The problematic part, if we have the situation for this phi equal to p4, and we cannot exclude the situation that our diffusion hits this point 0 along this ray, effectively. This means that eta 1 divided by eta 2 tau epsilon converges to some c. And for instance, if you look even at a situation where alpha is equal to 1 and the original coefficients to the operator, and for instance the coefficients of the drift in the direction of phi, it behaves, this is phi equal to p2, and this is actually positive here and negative here. So it's kind of pushes here for lower phi and pushes here for higher phi. So this actually might mean that this point is stable in some sense, that its triple collision might happen. On this way, I try to mimic the proof of some stability results, classical stability results. I haven't succeeded as of now, but my original conjecture was that no triple collisions are possible in Harris flow, but now I actually think that there might be regimes or some curves along which these points can get so correlated that they hit zero simultaneously, because as eta 1 and eta 2 go to zero, they become more, and they might become correlated or might not. It depends exactly on the situation. Here, they are not correlated if they hit zero along axis, but here they actually become correlated. And maybe it even depends on alpha, alpha being the threshold being alpha equal to 1, exactly. Because of fundamental diffusion, if you just consider the eta 1, alpha equal to 1 is exactly the place where 0 becomes a regular point instead of an exit point in the terminology of Feller. So what I'm intended to do, I want to try to clarify something about these points and these endpoints. And unfortunately, this is effectively all I have for today.
Okay.
But I think this whole idea of Kosminski is very nice, because it's very natural to consider something happening uniformly. And it leads to very beautiful and applicable results.
But this is only a sufficient condition, yes? When we have maximum.
It depends on the, so for instance, here we have minimum if we want repelling.
Mm-hmm.
It effectively depends whether you want this to be integrable or not integrable. If you want it integrable, as it goes into the denominator, you use minimum. Otherwise, you use maximum, etc.
Yes. So
Sufficient, sufficient.
yes, in both cases, it's sufficient condition, yeah?
Yeah, yes.
Yes. Okay. Maybe somebody have comments or questions, please. I remember that we also discussed the idea to approximate the Harris flow with non-smooth covariance, as you showed in the beginning, like exponent minus absolute value of x in power alpha, by the Harris flow with smooth covariance. And just to look on the behavior of trajectories, does it work, or it is the same?
It's not clear how to draw the conclusion, because you can get even Gaussian, like in the sense of Kunita flows, to do that.
Yes.
But those functions that you are using, they are going like to converge to delta functions in some sense.
Yes, yes, exactly. And maybe continue our yesterday conversation on different things. Why not to try to understand the possibility to blow up for density, for one point density? Yeah. Yeah.
This is an interesting question. So I think that the proper way to do it, and I kind of hope one day to get to there, is to do a transformation into Bessel process.
Mm-hmm.
And for Bessel process, people have already they have developed actually parametrics method for Bessel process.
Mm-hmm.
And then you can translate back using this time change.
Mm-hmm.
But the problem with those calculations, they don't seem easier than this, to be honest.
Yes, yes. Yeah, of course, I understand the problem. Uh, just another.
At least what I hope to achieve, that I can make totally rigorous this final statement that there are only a finite
Mhm,
number of regimes where you can hit,
mhm, mhm,
and do this transfer from linearized version to the original version. This is also interesting, and I think one should try to work in the spirit of this paper mentioned by Klipenko, Rasov, and Pavlukevich.
Yeah, it seems that it is the right way. Why not? Yeah, it is interesting.
Because if you have this eta 1 divided by eta 2, you can do effectively anything with it good from start. Because if you want to transform it into something, these are different clocks here and here.
Yes, yes.
So even in this case, like it
So
does.
also, I remember the idea that we can, because we just want to discuss actually one point, we discussed this angle point. We can change time and discuss the process on the all real line. And instead of discussing the limiting behavior at the point zero, to discuss its behavior on the minus infinity.
Yes, effectively, I think, well, I'm pretty sure because I checked just recently that Gikman-Skorokhov did this exactly. They established
Yeah.
asymptotic behavior at infinity, and then they...
Yes, and then came back. Yeah.
Yeah, but the power
What
of this
happened?
tests they developed, they are written in terms of the original coefficients in effectively uniform way. So it's still going to be pretty much the same calculation after the time change. You change your variables, but you arrive exactly at the same integrals, effectively.
Yeah.
And the problem here is that you have this two direction, and if you try just uniform as did Kosminski over phi, it doesn't answer fully. Because you can revert phi and rho and do this whole analysis by trying to speak about rho, this plus on plus zero from zero to plus infinity, and it still doesn't work for zero.
So don't you think that maybe these conditions max and min are too restrictive?
Yes,
Yeah.
obviously.
Yeah.
So my original idea is that maybe I can do some weighted instead of this
Yes.
maximum and minimum. I can introduce in the way sometimes like the Stratonowicz integral is defined. Instead of taking one half, you do the integral
Yes.
from. So my original idea was also to introduce this additional weighted integral that weights it with some in some way that can eat this rho minus one or these problems in terms of cosinus. I still think that it might be doable, but as of now, I kind of stuck for any
Also,
alpha not equal to one.
I see. But also, I think that originally, even Khasminsky paper was based on this winner idea with capacity when we have
No,
no.
no.
But why not? Why not to check this
Capacity.
just to have like some rings near zero and to check how fastly we reach every ring.
Yes, there is even a paper, I think, by Koenig on this
Mhm.
stuff. It doesn't work in this case particular.
Yeah.
Yeah, but there is,
So
yeah, I
so
think it's
so
also
so Koenig,
consideration.
Wolfgang Koenig, yeah.
Yeah, F. Koenig.
Yes, yes, Wolfgang
I
Koenig.
think
Yeah.
it's him.
Yeah, it looks like it also is a very working technique.
Yes, but the problem as soon as you get these, just technically, you've got these expressions. I think if I ever found a way to do this weighted stuff here, it should
Yes.
answer.
Oh, I see. Okay. Yeah, it's reasonable.
Because obviously, but again, the main problem might be that it can actually hit zero simultaneously for both coordinates. And given that this is exactly the drift that pushes here and pushes here, this might be the true.
It depends how fast.
How fast, yes. And we have this moving, this mixed coordinate, etc.
Okay, thank you for interesting talk.
Thank you.
It seems that this can be done, this problem can be solved in this direction, and it will be
I hope.
an interesting step in understanding of the structure of Harris flows. Okay, if there are no questions or comments, then
I'm sorry, I have to say this. It's not even about Harris flow. It's just about this degenerate diffusions, even in some sense.
yes, but you see, then it will very change the description of usual approach of description of the stochastic flows, because usually we have just a picture when, for example, well-known Aratia net where we have points 2, 2 at the slope. Yeah. But
Mm-hmm.
now we will have a more rich picture. It is interesting. Okay. If there are no any other questions or comments, then thank you again. And Georgi, do you know who will be next speaker?
Next speaker is Adam Bobrovsky.
I think that it will be diffusion on graphs, something like this. Yeah?
Yes, analytical description.
Okay. Okay, good. Thanks everybody, and bye up to the next week. Bye.
Goodbye,
Bye.
everyone.
Thank you.
Bye.